I'm Mr. Ambrose, and this is the fundamental counting principle. The fundamental counting principle helps us to combine things and make our life easier when it comes to examples like license plate possibilities, sandwiches we can order at Subway or any other restaurant, how many outfits can I wear based on the number of clothes I own. So it just makes our lives easier, and we'll see how. So let's say that I have 4 shirts, and I have, let's see, white, black, gray, and make all the letters different. Red, let's say red. So I have a white shirt, a black shirt, a gray shirt, and a red shirt. And then I have 3 pairs of pants, which are either blue or, I don't know, maybe green. That'd be kind of weird. But let's say I have green pants. And let's say I have yellow pants. And then for shoes, my options in my wardrobe are black or white. Okay? I have a few more pairs of shoes than that, but not too many more. If you have any more than I think 6 girls, I'm talking to you, you're crazy. But I have a wife and she has a lot of shoes, so I'm okay with it. So I have 4 shirts, 3 pairs of pants, and 2 pairs of shoes. The question is, how many different outfits can I wear? Well, I could write it out like this. Let me write it this way. So I could write W or B, G, and R. So white, black, green, and red are my options for shirts. And then for pants, I've got blue, green, and yellow. So I got B, G, and Y. And I'm going to write this for all the different shirts I could wear. This basically represents the fact that I could wear blue, green, or yellow pants with a white shirt, with my black shirt, with my green shirt, or with my red shirt. And then for the shoes, my 2 options are black or white, black or white. And this gets a little tedious, but I promise you it'll all be worth it. So this will go with this, or this, or this, 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 this. You get the idea. I'm running out of room. Oh my goodness. Oh my goodness. What am I gonna do? You get the idea. So this, by the way, this thing that I just drew is called a tree diagram. You can kind of see it looks like maybe branches coming out of a tree and getting bigger. What it represents is all the combinations I could wear with this wardrobe I described. So the first combination, we won't go through them all, but the first combination I could wear is a white shirt with blue pants and black shoes. I might not look super good, but I could wear it. So I'll write that as W, B, B. So white, blue, black. And if I do this for all the different possibilities, which we won't write out, there's actually going to be 24 different possibilities. So 24 different outfits, which is pretty interesting. I might not want to wear them all because they might not all look good, but I could wear them. They're possibilities, right? I could possibly wear this many clothes or this many outfits based on this many clothes that I own. Okay? Now the question is, did I have to do all that work? You guessed it. Nope. There's always a shortcut in math. Not always. I don't like saying always or never, but there's usually a shortcut in math, and here it is. It comes from the fundamental counting principle. So let me erase all this mess. The fundamental counting principle says that if I have 4 shirts, 3 pairs of pants, and 2 pairs of shoes, all I have to do is multiply those numbers together to figure out how many different possibilities I could wear. 4 times 3 times 2, that's 12, times 2 is 24. How much easier that was than having to draw that tree diagram. 24 options. Now, don't get me wrong, tree diagrams are very, very, very helpful in certain problems, but in simpler problems like this, you don't need to draw it if you don't need to. You could simply use the fundamental counting principle, which says 4 times 3 times 2 is 24 options. So in general, the fundamental counting principle says this. If you have m items in one category and you have n items in the other category, to figure out the total number of combinations you can make, you simply multiply m times n. And that's for 2 categories. In our example, we had 3. We had shirts, pants, and shoes. So the same rule applies. We just multiply by the next number. Okay, so in general, it would be m times n times the next letter is o times p. And this could go on for as many number of categories you have. You just multiply them all together. As you can imagine, with a lot of items, this gets really, really big, really, really fast. And you wouldn't want to draw a tree diagram because that would just take way too long to do. So this simplifies things a whole heck of a lot, which is why it's great. Okay, so that's one example. Another example. So I like Subway. Not the best, but I go to Subway. It's pretty good. Suppose I went to Subway and I had 3 options for my bread, 4 options for meat, 5 options for cheese, and 7 options for veggies. Now, if I could only pick 1 from each of these categories, so I can only get maybe like 1 vegetable instead of all 7, and a lot of you are probably saying, I don't like vegetables anyway, I don't get them anyway. Well, let's just assume for the sake of this problem that you can only pick 1 vegetable and only 1 piece of cheese, or type of cheese, 1 type of meat, and 1 type of bread, right? So the number of possible combinations of sandwiches that I could choose from with these numbers is just going to be, by the fundamental counting principle, 3 times 4 times 5 times 7. And if you do that out, you get 420, believe it or not, possible sandwiches. Now, I way oversimplified the real menu at Subway. Subway claims to have something like, I think 68 billion, I think it's billion with a B, different sandwiches you could order, which is insane. But they didn't sit there and draw a tree diagram to figure it out. They used probability like this to figure it out. Okay, so that's another example. Another example I like to look at is license plates. So a lot of states have license plates that look like this. So there's 3 letters, and then there's 3 numbers like that. The question is, how many different possible combinations of license plates could I come up with? Using the fundamental counting principle, I could figure it out. And there's 26 letters in the alphabet. So that means there's 26 possible letters I could put here, and here, and here. Meaning 26 times 26 times 26. And then 10 numbers, right? 0 through 9 is 10 digits. So this is 10 times 10 times 10. And that's a really big number. But it's a good thing I figured it out before, because it's 17,576,000 different possible license plates. And that's good for a lot of states because most states have less people than that in their entire population, let alone the population of people who are driving. Okay, so that's why they use random letters and numbers in weird combinations like that. It's because it just gives a lot of different possible license plates, and they know they're not going to have any duplicates. Hopefully that helps.